Hello, and welcome to Pre-Calculus Review Part 2 for Applied Calculus. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Applied Calculus used to be called Business Calculus. I suppose maybe it was always called Applied Calculus, and I just used to call it Business Calculus. But it is for the non-science majors, non-engineering majors, anybody that needs calculus. This is a review of some of our algebra that you should know and you need to know before you get more in-depth into calculus, applied or not. Start with rational expressions. Rational expressions is the fancy math term for saying some fractions. And really, they're not fractions. Fractions are ratios of integers. But rational expressions are ratios or fractions created by polynomial expressions, or algebraic expressions. Basically, they're fractions. So if, let's pick the right thing here. If P, Q, R, and S are polynomials, then when we multiply P over Q times R over S, we'll multiply straight across. P times R over Q times S, as long as Q and S are not 0. An example to the right here, we have 2x over y times x plus 1 over y minus 1. We'll just multiply 2x times x plus 1. We'll multiply y times y minus 1. And that'll give us our final answer. In division, p over q divided by r over s. Instead of dividing, we multiply by the reciprocal. So the one that follows the division sign is called the dividend. It's what we're dividing by. The dividend is the one that gets flipped upside down. So P over Q times S over R, and then we revert to an earlier problem. And again, an example here to the right. Let me move this back over so you can see the whole thing. If we're adding and subtracting rational expressions with equal denominators, very important, remember adding and subtracting, they're the ones that require sameness. So as long as the denominators are the same, all we do is add the numerators. So 2x over x plus 2 plus 6x over x plus 2. That's just going to be 2x plus 6x all over x plus 2. And then we'll combine our numerator, 2x plus 6x, simplify that to get 8x. And our denominator stays the same. Very important. Our denominator stays the same when we're adding and subtracting fractions. It's that idea of sameness that I talked about in the Pre-Cal Review Part 1. Subtracting two fractions with common denominator already, equal denominators, same thing. We just subtract the numerators. Make sure that negative sign goes to everything that follows, though. If you had something more than just y, if you had y plus 7, you'd want to make sure that that negative sign went to the y and to the plus 7 to make sure you subtract the whole thing. Equal denominators, fairly straightforward. When you're adding and subtracting rational expressions with different denominators, you must first find the common denominator. It could be any common denominator, but to cut down on the amount of work later, go with the least common denominator. To find the least common denominator, you'll want to completely factor every denominator that you're looking at. From those factors, you want to form the product of the different prime factors, so let's call those unique prime factors that occur in each denominator. Each prime factor should appear in the LCD the greatest number of times it appears in a single denominator. Alright, so completely factor your denominators. Then take each unique factor, the greatest number of times it occurs in a single denominator, and you can find your least common denominator. Other than just straight up rational expressions, we could have what are called complex fractions. And a complex fraction, or an other algebraic fraction, might be something of the form 1 plus 1 over x over 1 minus 1 over x. It's a fraction within a fraction. So an algebraic expression that has another ratio either in the numerator, in the denominator, or like this one, in both places. And as I was giving this lecture in class before I chose to record it, I did method 1, but it wasn't called method 1, it was called this. And my students looked at me like, huh? So I'm going to show you two methods. All right? Pick whichever one you like better, whichever one makes sense to you. So if I want to simplify a complex fraction, what I want to do is I want to make it so the numerator doesn't have any fractions and the denominator doesn't have any fractions. I only want one fraction bar in this whole thing. So I look at my numerator. 1 plus 1 over x. Well, 1 over x is a fraction, algebraic expression. I'm going to use the term fraction. In order to add something to a fraction, I have to have a common denominator. So I rewrite 1 in fraction form with the denominator that I want. Right? How do I get 1 that has a denominator of x? That's x over x. Same thing here. I want to subtract something that involves a fraction, so I'm going to get a common denominator. 1 is x over x. So in the numerator, I'm adding two things with the same denominator, so I'll add their numerators, x plus 1 over x. In the big denominator, x over x minus 1 over x, I'll subtract my numerators, x minus 1, keep my denominator over x. So this is the method of finding a common denominator in the numerator, finding a common denominator in the denominator, and then combining those fractions, because now when I have one fraction divided by another, I can turn that into multiplication. Remember, the dividend, the one we're dividing by, is the one that we use the reciprocal. So instead of x plus 1 over x divided by x minus 1 over x, I'll now have x plus 1 over x times x over x minus 1. The x's cancel out. My pen died. I have to use my finger. Let's see if this will work out. X's cancel out. And I'm left with a completely typed wrong equation here. This should be x plus 1, and that should be a minus. Let's make it in blue. Minus 1. Sorry about that. I will make a note and change it where I can. So what's the second method? Because that seems so stressful. So take a look. Take a look at all the fractions that are part of this fraction. And I see 1 over x and I see 1 over x. My common denominator is x. Right? It's the only denominator. So how about, instead of looking at just the numerator and then looking at just the denominator, let's deal with this all at once. If the common denominator for all the fractions in this entire expression is x, how about I multiply x times everything in the numerator and x times everything in the denominator? Alright. X times 1 is x, plus 1 over x times x, that's x over x, and we know that's 1. 1 over x times x is x, minus sign. 1 over x times x is 1. So we did the same operation, two different operations, the same twice. X times 1 and x times 1 over x. The only difference are the signs in the middle. Personally, I like method 2. I use this probably more frequently than the other one, but students seem to like common denominators and that sort of thing. Use the method that works best for you. Rationalizing. In part 1, we talked about just simple rationalizing of maybe a square root of x in the denominator or a cube root of x in the numerator. But what happens if you have a full expression, something more than just a term? If I want to rationalize the numerator of the square root of x plus 3 minus the square root of x all over 3, and this is definitely something we'll see later in calculus, if I want to rationalize the numerator, I want to multiply appropriately so my numerator no longer has a radical. And when we get our answer, you'll kind of see why it is a kind of cool process. So I take my original expression, the square root of x plus 3 minus the square root of x all over 3, and I multiply appropriately, which means I multiply by the conjugate. I use the conjugate because the difference of squares formula. Because I know that a minus b times a plus b is a squared minus b squared. The difference of squares formula is one of the most important formulas you can have for factoring, but don't forget it goes the other way also, multiplying the products. So I'm going to multiply by the conjugate of the numerator, But I'm going to do it both to the numerator and the denominator because I just can't start randomly multiplying. I have to multiply by a form of 1, something over itself. That way I don't change the problem. But remember, the reason we multiply specifically by the conjugate is so I'll have the square root of x plus 3 times the square root of x plus 3. The square root of x plus 3 times the square root of x and minus square root of x times the square root of x plus 3. Those are going to cancel out. Positive times a negative is negative. Square root of x times the square root of x is the square root of x squared. Notice in the denominator, I'll put 3 and then parentheses, whatever I multiplied by. You could multiply it out. I encourage you not to until the final step, and we'll see why. Now, we multiplied by the conjugate specifically so the square root and the square will cancel out and give us our radicand, x plus 3, minus sign. Square root of x all squared is x. Still have my denominator, and I still write it in factored form, not until the very end will I choose to multiply. X plus 3 minus x, my x's cancel out. I'll have 3 over 3 parentheses, square root of x plus 3 plus the square root of x. And this is why I didn't multiply my denominator. 3 over 3. This 3 cancels this 3, and I'm left with 1 in my numerator, and this is how I think of it. 3 is the same as 3 times 1. So I'm canceling this 3, and I'm left with the 1 in the numerator. 1 over the square root of x plus 3 plus the square root of x. Why do we care? Why would we need to do that? Keep watching the applied calculus videos and you'll see. Inequalities. Properties of inequalities are kind of handy. If A is less than B and B is less than C, then A must be less than C. Think of this as left of on a number line, and you can see exactly why it must be true. If A is less than B, and I add the exact thing to both sides, I've scaled everything just right, it slides along, so it's all good. The inequality remains the same. If A is less than B, and C is positive, so it's not in 0, it's not negative. If C is positive, then the inequality remains the same. So I can multiply both sides of an inequality by 2. I can multiply both sides of an inequality by pi. I can multiply both sides of an inequality by 3,472. It doesn't matter. The inequality is going to stay the same. What changes is when I multiply by a negative value. When I multiply by a negative value, now my inequality switches. And the reason for this all comes down to our number line. Remember, our number line has positive numbers to the right that are increasing, negative numbers decrease to the left. Think of less than as left of. 1 is to the left of 2. However, in the negative numbers, negative 2 is left of negative 1. So it changes the order when I change my signs. And that's the whole reason for switching the direction of the inequality when you multiply by a negative. The absolute value. A lot of people learn absolute value makes it positive. That's not true. The absolute value of a number A, denoted by these two little lines here around it, it's defined by a piecewise defined function. So it's the first piecewise defined function we ever learn, but we don't necessarily learn it in the piecewise form. So the absolute value of A is A, as long as A is 0 or positive. It doesn't do anything to a non-negative number. What the absolute value does is if you are given a negative number and you take the absolute value, then it changes the sign. So it doesn't make everything positive. What it does is it changes the sign of a negative number. And I know on the surface they sound the same, but there's actually a huge difference. We think of the absolute value as a distance, the distance from 0 to A on a number line. And so distance, I live in Las Cruces, New Mexico. Don't hunt me down. I live in Las Cruces, New Mexico, and I drive to El Paso, Texas for work every day. Go Miners. And it's, wow, I'd really have to think about it, like 48 miles from door to door, I think. But at the end of the day, when I leave UTEP and I come back to Doña Ana Community College, which is umbrella of Mexico State University, go Aggies, it's still 49 miles. It's not plus 49 one direction and minus 49 the other. It's just 49 miles. And that's what absolute value does. It looks at, let's not care about direction, just how far is it. Properties of absolute value. To solve an absolute value equation of the form the absolute value of A equals B, where A is some expression, maybe 2x minus 3 inside the absolute values, and B is any real number. If B is less than 0, there's no solution because the absolute value will never equal a negative. If B is equal to 0, I just have the absolute value of A equals 0, and I solve. A equals 0 and solve for x. But if B is positive, these two lines remind me I have to solve two equations. The absolute value of A equals B, if the absolute value of A equals B, I have to solve A equals B and A equals negative B, as long as my B value started out positive. And property 5 is the reason for that. It's because the absolute value of negative A is the same as the absolute value of A. We know that the absolute value of negative 3, right, takes a negative input and changes its sign, so that's negative 3, which is 3. That's the same as the absolute value of 3. So if I have a positive number, so B equals 3, I don't know if once I did the absolute value to it, I don't know if it started out as 3 or started out as negative 3. I have to allow for both options. The absolute value of a product is equal to the product of the absolute values. The absolute value of a quotient is equal to the quotient of the absolute values, as long as I'm not dividing by 0. And this one's important, right? Because multiply and divide, things are kind of good if you look at the order of operations. P, E, M, D, A, S. I'll even write them up here. P, E, M, D, A, S. Multiply and divide have a level where you can go down. So everything's fairly straightforward with multiply and divide. When it comes to add and subtract, there's nothing lower. So sometimes our rules get weird when it comes to add and subtract, and that's what we see here in property 8. The absolute value of a sum is less than or equal to the sum of the absolute values. Alright, so the absolute value of a sum is less than or equal to the sum of absolute values. And we see an example here that shows where it's true. If A and B are both non-negative to start with, that's where we have our equal to. If either A or B is negative, then we have the less than portion of the property. That's it for Pre-Calculus Review Part 2 for Applied Calculus. Stay tuned for more.